Dr. Emily Hogan and a PhD about 3 years ago, and we'll talk about very interesting stuff related applying combinatorics to the real world. As usual, we're going to take Emily out to dinner at the usual place. If you'd like to join us, let me know immediately after the talk.
All right, thank you for the invitation. I'm really glad to be here. So I work at the Pacific Northwest National Lab, and all the work that I do is applied, but I do a lot of pure math to get to that application. So I'm going to talk today about some partial order results that may seem really easy, but we haven't actually seen them. We've looked for them in literature, but we haven't seen where they've been used. So hopefully this is some new stuff and you'll learn some things. So the application is motivated by ontologies. And this is a philosophy term, but we use it to basically mean a collection of entities with relationships. So this is really just a graph, and the relationships are labeled. So there's different types of relationships. And the most common one that you see in these kinds of things is the is-a relationship. So for example, you can have the concept of mammal and the concept of bird. And above that, you have animal. And we have these is-a relationships between mammal and bird and animal. And you can further go down and put like cat and dog, and maybe eagle. And so this would be an ontology with just a single relation, which is is-a, and these can often be called taxonomies. And you can see that in this taxonomy, and in particular this is-a relation, you get this partially ordered structure. So in particular, what we want to study is the partial order structure. So that's kind of a little introduction into why we are actually studying these things.
So the entities are all of those things? Animal,
Yes, so
mammal, bird,
these are all the entities, and then anything that there's a line between, there's a relationship. And so you could add other relations to the diagram. This is a single relation, but maybe you could say has fur, and the dog also has a has relation over there, and so you can put all these different things together, and what you get is basically a knowledge base, a knowledge system. It's a way to organize knowledge, which is kind of the spirit of the philosophical definition of ontology, but this is maybe more of a database take on the concept. So these show up in a lot of different ways. One of the most common is the gene ontology. This stores information about gene processes and what different proteins do or things like that. And so the different processes might be in there annotated with the proteins that match them. And then there's relationships between the processes themselves.
Also, for the OIS could be used, the sequences or the types.
Maybe, yeah. There's metadata in there that could be used for sure. Okay, so partial orders are very common. Everybody probably knows what a partial order is, but just in case, quick definition, partial order, or poset, partially ordered set, is a set P with some less than or equal to relationship, so that for all P, Q, and R in my set P, I have that P is less than or equal to P, so everything is reflexive. P less than or equal to Q and Q less than or equal to R implies P less than or equal to R. Transitivity, and then finally P less than or equal to Q and Q less than or equal to P implies that P equals Q. So you can't have something below and above. So these are the axioms of a partial order. And then we have in particular the cover relation, which is the curly less than. So if P is covered by Q, then there is no R in P such that P is less than R is less than Q. So Q is immediately above P, there's nothing else between them, and they're not equal. So this cover relation can be used to draw a poset in the Haas diagram. And this is just a way of visually representing a poset. So for example, I'm going to draw two different visual representations which are kind of going to motivate the rest of the talk. So if I call this top, this bottom, A, B, C, D, this is all the cover relation. So D is covered by B, D is covered by A, bottom is less than everything, and so forth. And then the second example, which is going to be different in one particular way, we have top, bottom, A, B, and C. So this is another cover relation Haas diagram, but I'm going to use it to motivate the rest of this. So you can see that in this diagram, everything kind of has a clear level of where it should be sitting. So this is kind of like level 0, level 1, level 2, level 3. This one doesn't really have that because B kind of sits between levels. So this is captured by a rank function. So given some poset P, we define function row from set P to the natural numbers so that row of the top is 0, and if for all A covered by B, row of A equals row of B plus 1. So as I move down, I add 1 to everything. And this is called a rank function. Relation called the rank function because it's kind of uniquely defined. And if row exists, so you can't always define this, but if it does exist, then the poset is graded. So you can see over here the rank function would be exactly what I wrote, but I'd have to copy it over here to the other one. So everything is here as level 1, level 2, level 3, and you can see here that we can't really do that. We can define this as 0, 1, 2, and 3, but B can't be 1 because then this is not a difference of 1, and it can't be 2 because then this is not a difference of 1. So the goal in the application is to be able to visualize posets, visualize these ontologies, because if you want to know kind of what the structure of your knowledge base looks like, you need to actually be able to look at it. And so we want to, first of all, try to figure out what level to put things on. So that's going to motivate the need for saying, well, is this 1? Is it 2? Is it 1.5? You know, it's really, it couldn't be less than 1, right? We don't want to put this guy way up here. We don't want to put it way down here. So we want to put it somewhere in between 1 and 2. So the natural thing to do then is to say, well, it could be anything in between. It could be the interval between 1 and 2. It could be the rank of this vertex. Okay, so let's see. Oh, I just wanted to mention that you may have seen rank going the other direction where you start at the bottom with 0 or 1 and going up. Obviously they're equivalent. But that is more standard to go from bottom up. But in ontologies, we care really about the root, the thing that everything inherits from, and so we want that to be defined as level 0. And we often don't have a bottom. Okay, so if I want to put intervals on these as ranks instead of integer values, well, you can't really do the same definition because what's adding 1 to an interval? It doesn't really make sense. So instead what we'll say is, I want intervals to be increasing as I go down. So we need to know what increasing means for an interval. We need to have an order relation on the intervals. So if I have interval xy, there's a couple of different ways that I could define an order relation. I could say what I'm going to call the strong order. And this is when y is less than or equal to z, or when x equals z, y equals w. So if the intervals are exactly equal, or one is completely before. So the intervals on the real line will look something like this. This one finishes before the second one starts. There's the weak order, and this is when x is less than or equal to z, and y is less than or equal to w. So this looks something like that. So this one starts before, the first one starts before the second one, and it finishes before the second one. And then we have the subset. And of course this one is exactly what it sounds like. The first one, so this would be the first one, is contained within the second one, the bigger one, and so we have a subset relationship. Guess I can move this thing down. So those are three possible ways that I can order intervals if I'm going to say something about a rank function being an interval instead of just a number. One interesting fact that I'll just say is that two intervals are always in either weak order or subset order, or both. So if there is equality, so if you have this interval and this one, this top one is contained in the bottom one, but it's also weakly less than the bottom one. But if you don't have equality on the endpoints, then you're either in the weak order or you're in the subset order for any pair of intervals. So this is called conjugacy of partial orders. Just something we ran across as we were doing this work, and I thought it was interesting. Okay, so now I'm going to define for you an interval valued rank. So given our poset and an interval order, this is one of those three, or they're duals, so greater than in any of them. We define R according to this interval rank, or sorry, this interval order. From the set of the poset to the set of intervals of natural numbers. We say that our lower star of P and our upper star of P is an interval rank function for this order if for all A less than B in P, we have R of A contain or less than R of B. So it's basically just saying that as long, when A is less than B, the interval rank of A is less than the interval rank of B. So if we go back over to our example here, I'm going to erase the ones that I've already got on here and write a couple of others. So maybe I can use a color chalk here. So I could say, for example, 0, 1, 1, 2, 2, 3, 3, 4, and here I could say 1, 3, and this one would work for the strong order. So 0, 1 is less than 1, 2 in the strong order, and because we're looking at the reverse of it, we're increasing as we go down, and so all of these relations are true in the strong order. We could do a subset one as well. The one that I want to really highlight is the weak one. So this is 0, 0, 1, 1, 2, 2, 3, 3, and 1, 2. This is basically the intuition that I gave you at the beginning of how we would really want to rank this thing if we were using the real rank. Okay, so we could also do something degenerate. We could say this is 1, 3, 2, well, no, sorry, 0, 0, 3, 1, 3, 2, 3, 3, 3, and let's say 1, 3 again. But because we have the same thing in the second coordinate, we really don't want to count this. It's still a valid interval rank, but we don't really want to count it as one. So we need to make a second definition. We're going to call a strict interval rank. So an interval rank function is strict if the two functions themselves are strictly monotonic. So we have to always be increasing in each of the two coordinates in order to be a strict interval rank function. So all of the ones that I gave you except for that last one were strict interval rank functions. And so this kind of captures that intuition. And now the one that I gave you for weak is one possible value or one possible evaluation of the function for the weak interval rank, but there are possibly others. So we have picked a canonical one because we think it makes the most sense, and it's the one that I just showed you. So I'm going to define, first of all, so this is the upset of A, all the values, all the things in the partial order that are bigger than A. Also known as the filter and ideal of a poset. And then you can also define the height of a poset, or really a subposet. So if you have some subposet, you can look at its height, basically the length of the longest chain from the top to the bottom would be the height. So given those things, we can define our plus of A to be the height of the upset of A minus 1, and then the height of the full poset, so H without anything is the full thing, minus the height of the downset of A.
When you measure height, do you count edges or vertices?
You count vertices. And so this is called the standard, or we called it the standard interval rank function, and it is for the weak order. You can create a similar one for the subset order that's also kind of canonical, but we like the weak order the best. I think it's the easiest to understand. Well, I decided to erase instead of pull down. Okay, so a couple of things to show. Well, first of all, that R plus of A is an interval. Right? We better have that this is less than that, or it's not going to be an interval. So you can see that the height of the downset of any vertex plus the height of the upset of any vertex had better be less than or equal to the full height plus 1, because that's everything below it plus everything above it, and then itself, because it's in both sets, is counted twice. And if you rearrange things, you get exactly this relation, the height of up A minus 1 less or equal to full height minus the height of bounding. So it's certainly interval valued. The second claim, number 2, is that is strictly monotonic. So here we can say if A is strictly less than B, then we know that the upset of A has to contain the upset of B, and strictly contain, right, because A is in one but not the other. And so this means that the height of the upset of A is greater than or equal to the height of the upset of B. But of course, because A is below B, when I take the upset of A, I know that I have at least one more thing. So if this is B, and A is here, there may or may not be other things in between, but the height is going to increase by at least 1. And so that I know that this guy, when I go up or down, when I go down, it's going to increase by at least 1, and so this strict monotonicity is captured. And you can do the same exact thing for the other side for this one. So we can see that both of these functions are strictly monotonic, and it's interval valued. And in a paper that we just submitted, we proved that basically if you have any interval valued function that is strictly monotonic on both of its endpoints, then it is an interval rank function, always, for some interval order. So if f is a function from p to the intervals with these two strictly monotonic then actually this is an if and only if f is a strict interval rank function for one of these 4 orders. So because we know that they're strictly going down, we can say that it's, in this case, it's for the weak order decreasing. So we know that this is an interval rank. And then something else that we found that's interesting that kind of motivates why this is canonical is the following other proposition, is that R plus is somehow maximal with respect to the subset order. So this means that for every strict interval rank function for the weak order with R plus of P, R of P, always contained in intervals between 0 and height minus 1. We have R of P is a subset of R plus of P. So whenever I look at one of these interval ranks, one of the interval values, it's the biggest that it could possibly be. So it encompasses the most that it possibly could in terms of what level could I actually put these guys on. And the intuition here is basically that as I go down in my partial order, I'm always adding exactly 1 to the first column, and as I go up, I'm subtracting exactly 1 from the second, and so the first coordinate is the smallest it could possibly be, and the second one is the biggest it could possibly be. So that's the intuition there.
I have a question.
Yeah.
What are some examples where this applies? Because all the posets I know are graded.
Are graded, yeah.
So what are some good examples of non-graded ones?
Anything in the real world that you find,
Yeah,
pretty much.
right.
So all of these ontologies that you see, if you throw a bottom bound on it, So for example, in the gene ontology, if you just draw some taxonomy, and we like to put bottom bounds on because it really shows you where things lie. Because something is too away from the top doesn't necessarily mean that it's close to the top, right? It could be at the very bottom and really more related to the bottom than it is to the top. So if I put an artificial bottom bound on, all of a sudden we get something that's not graded anymore. And so now we want to kind of see, well, if I really wanted to display this, I would probably put these guys farther down, more like that, but not as far down as these because these have longer chains going up. So this is more for display to show people what this looks like. Now this doesn't say anything about the horizontal display. That's tricky, and that you need something more sophisticated than this to show what it's going to look like. But this is kind of the motivation in the real world.
But also family trees are often
Yeah?
linked. You can, family trees.
Yeah,
Often
sure.
you can marry your uncle.
Sure. And I guess there are examples in number theory.
Yeah, so anything in the real world is typically not as nice as anything that a mathematician would think of in a pure space.
You're
These are
saying
not
we-
lattices, these are not, well, they could be lattices.
You're saying we don't live in the real world?
No, not at all. I'm just saying that the real world is much more complicated than can be encompassed by some of these things. Okay, so I wanted to transition to talk, I'll leave this up here, to talk about another aspect of this. So this is what we're going to use now as interval rank for the rest of the time, because we like this one so much. And we noticed that the structure of the intervals, because of how we define the interval rank function, is itself a partial order. Right? So if I look at the intervals, because we define these interval orders, the weak and the strong and the subset, I can actually partially order the intervals that I get when I do the interval rank. So what you can do then, with a small example, is recreate. So I'll give this example again. Oh, no, I'm actually going to give it a different example. One that's a little bit more complicated. So we have this one long chain. We have a couple of guys over here. And the bottom, and there's one over here. So if I did the interval rank, the standard interval rank, I get 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4 going down the bottom. This one, the height above is 2, so I put a 1. The height below is 1, 2, 3. Subtract that from 5, because that's the total height, and I get 2. This becomes 2, 3. As does this, you can see these are basically interchangeable elements because they have the same parents and the same children. And then over here, this is 1, 3. So we could take these intervals then and order them and see what happens. And again, because this is for the weak order, we're going to order these with the weak order. And we end up getting 0, 0, 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3, and 4, 4. And this forms our partial order of the new intervals. And these, because of the definition, because we have to have A less than or equal to B, implies R plus of A with the weak order greater than R plus of B. We know that the relation over here in